Hello everyone and welcome to yet another video. My name is Stace, I'm the technical evangelist at Varnish Software, and today we're going to talk about cache invalidation in Varnish. If you know Varnish, you'll appreciate the fact that serving objects from the cache is important for your performance. However, removing objects from that cache in a timely fashion could be just as important. Allow me to explain for just a minute before we kick off with the actual video. If you have an object in the cache and you serve it to your end users, but there has been an update at the origin, those users will never see it until the content expires. Do you really want to wait for that? Imagine a situation where there is breaking news, a really important news item that is not able to be published on the website because the cache has an old version. You obviously don't want to take that risk, and you want to ensure that when content updates happen at the origin, that Varnish is made aware of that, so that it removes the relevant objects from the cache and replaces them with the new data. And Varnish has a couple of mechanisms to do that, such as purging and banning, X key, Y key, and a couple of more niche mechanisms that we'll cover as well. So enjoy the video, here we go. In a normal caching workflow, Varnish sits in front of the origin web server and receives incoming HTTP requests from the client. It forwards some of those requests to the origin if the content is not stored in the cache. When the origin responds with an HTTP response, Varnish stores that in the cache and delivers it to the requesting client. The goal is for the next request not to hit the origin and to be immediately served from the cache. When we want to invalidate content from the cache and remove certain objects from Varnish, the origin can actually send an HTTP purge request to Varnish. Could be the origin, could be any other client sending that request. And then Varnish will respond with a 200 purged. The logic to perform those purges needs to be implemented in VCL, and here's an example of what that might typically look like in its most simple form. We start off by overriding the VCL receive subroutine, which is required because the standard behavior has no logic for the purge request method. There's an if statement that checks whether the request method equals purge. If that is the case, we immediately exit the subroutine by calling return purge, which in its turn will call the purge logic and remove the object from the cache. The output is synthetic output that was directly triggered by the return purge call. Synthetic means that it didn't originate from an origin response, but rather was composed by Varnish itself. It's formatted as HTML and is composed in the VCL synth subroutine, where the HTML string is created and where variables are interpolated. Variables such as the response status, the response reason, and also meta information such as the request transaction ID. And these variables are easy to spot in the HTML output. 200 is our response status, purged is our response reason, and 32770 is our request transaction ID. Don't worry about the word error appearing in the output. This is merely a template that could be triggered for a variety of reasons. It could be that an internal error would also be using that same template. But remember, you have the ability to alter that template by simply overriding the logic in VCL synth. There are security implications related to cache invalidation. If we leave the purging interface open to the outside world, anyone can perform purges, which would result in a very low hit rate and potentially destabilize our entire environment. That's why we need to protect the purging interface using an access control list that contains a white list of host names, IP addresses, or IP subnets that are allowed to perform these cache invalidations. In our VCL logic, we add an if statement that checks whether the client IP address matches the ACL called purge. When that is not the case, we again return synthetic output, but this time around we do want it to be an error. We return a 405 statement with the message not allowed. And with these measures in place, we can now comfortably send a purge HTTP request, which uses the purge request method. The URL is /products, which is the page we want to invalidate. But of course, we need the host header as well, which is example.com. So in fact, example.com/products will be removed. We can convert this into a curl call if you want to run this on the command line. And then you could say curl -x purge, and the -x parameter is there to set a request method. So we're doing a purge call to example.com/products. Just so you know, you're not forced to use curl as an HTTP client. You can use any HTTP client you want. Potentially the HTTP client in your application framework or the integration that comes into your content management system that supports purging in Varnish. There are many benefits to using native purging in Varnish. The fact that it's so simple in terms of the mechanism is one of them. Also, purges take immediate effect
and are very easy to implement, both in terms of VCL as well as integration into the application that actually performs the purge calls. Using purging also has a couple of downsides, unfortunately. The first one I want to highlight is the fact that it requires knowledge of the URL structure for it to work. So you need to know the URL of every impacted piece of content that you want to touch. And on top of that, you need to perform an individual purge for every affected URL. And besides the limited feature set, the one that really stands out as a downside is the fact that a purge removes the object from the cache immediately. And ironically, that phenomenon was presented as an advantage at first, the fact that it takes immediate effect. Let me quickly explain why this is a downside. When the next request after the purge comes into Varnish, Varnish doesn't have an object to serve, so it forwards that request as a fetch to the origin. But when the content is slow, well, the backend fetch needs to wait. But at the same time, the end user needs to wait as well. And now that end user is inconvenienced. There is a more elegant way of tackling this and reducing the impact on the end user. And that solution is called soft purging. Varnish comes with a native Varnish module called Purge, which deviates from the native purging feature set. That module, or vmod as we often call it, has a soft function that performs soft purges. Rather than immediate object removal, it forces expiration. And it does so using this first argument of the function, which is called TTL, which is of the duration type. So you want to set that to 0 seconds to make sure that the object is marked as expired. And even though the content is expired, Varnish can still serve stale content as long as the grace value allows it. Grace sets the amount of seconds past the TTL objects can be served from the cache even though they're stale, while an asynchronous fetch is happening. And that really softens the blow for the end user. We can set the grace value to, for example, 30 seconds. The keep value is there to keep the object around, as the name implies. Even though the object has expired and it's out of grace, you do want to keep it around for what we call conditional revalidation. It is not asynchronous like grace, but it does have the potential of being faster than a regular fetch. When the response of a backend fetch contains an E tag, Varnish can store that E tag for later validation, but also forwards it to the client, who also uses it later on under the form of an if none match request header. And that's something web browsers automatically do under the hood. And Varnish forwards that if none match header to the origin, and if the origin is optimized for that, it can return a 304 not modified instead of a 200 OK without any payload. Given that the application is optimized for that, it will still be faster than a regular fetch. Calling the soft purge function in VCL can only happen in the VCL hit or VCL miss subroutine, which does change our logic a little bit. The first thing we do is import the purge module. The logic to match the purge request method is still the same, but instead of calling return purge, we call return hash to look the object up in the cache. And depending whether it's a hit or a miss, either VCL hit or VCL miss will be called. And in both cases, the custom myPurge subroutine is called. In the myPurge subroutine, we run the purge.soft function with all the attributes we need. And the result of the call is stored in rec HTTP purge, which is a numeric value that contains the amount of objects that have been invalidated. If the result equals 0, it means the object that we wanted to invalidate wasn't found, so we return a synthetic 404. But however, if we did succeed in performing a soft purge, we return a synthetic response with 200 as the status code and purge as the response reason. Besides purges, Varnish also supports bans to perform cache invalidation. And the main advantage is that it removes multiple objects from the cache at once. And it does this using a syntax called ban expressions. This is what a ban expression could look like. We're selecting all the objects that we want to match for invalidation if the object status is greater than 200. All the objects that match these criteria will be marked and eventually removed from the cache. And the expression syntax has multiple operators. You could be using a double equal sign to match a string. You can use logical AND operators to chain multiple expressions, or you can use a tilde to match a regular expression. And in this case, we're matching all the objects where the host header is example.com and where the URL starts with /admin. Invalidating content using bans requires adding the ban expression to the ban list, and you can do that using the Varnish ADM command and more specifically the ban subcommand. And the ban expression is attached as an argument. And while running bans using the Varnish ADM command is fast and doesn't require any VCL customizations, having an HTTP interface is also nice. In the VCL code, there's still similarities to the purge logic. We still try to match the purge HTTP request method. But additionally, we're doing an and doing an extra check. We're checking if the X invalidate pattern request header exists. And if it does, it contains a relevant part of the ban expression. Adding ban expressions to the ban list in VCL is done using the ban function. In this example, we're interpolating the X invalidate pattern request header, which contains the URL we're trying to match, and we're injecting that into the complete ban expression. We're also injecting the host header, which automatically comes with the HTTP request. And once we fired off that ban function call, we can return a synthetic response with a 200 status code and the message ban added. That message implies that the objects aren't immediately removed from the cache, but that the expression is added to the ban list and that the ban list is processed asynchronously. You might have spotted the other code, where we override VCL backend response and VCL deliver. We're creating custom response headers that will store in the cache, in the object, that actually contains request contexts, such as the request URL and the host header. Because the ban list is typically processed by a separate thread, there is no request context available. That's why we need to inject it. And we do that in the ban expression by not matching rec.url but object.http.xurl and object.http.xhost instead of rec.http.host. But that's just there for internal purposes, so at delivery time we just strip these custom headers off because the client has no business seeing them. And yes, just like with regular purges, with bans it also makes sense to define an ACL to restrict access and to enforce that ACL in your VCL code. Using the HTTP interface to issue a ban requires an HTTP request using the purge request method. The URL itself doesn't matter so much because the actual URL is encapsulated into the X invalidate pattern header. And the expression itself is /admin, meaning match all the URLs that start with /admin. And because the host header is mandatory, we're leveraging it in this case to only match objects whose host header is example.com. And again, the output is, as you'd expect, it's synthetic output that was composed by VCL synth, but instead of purged, we have ban added as the status message. And here's the corresponding example for bans where we convert this HTTP request into a nice curl call. We still have -x to define the request method, which is purge in this case, but we also have a custom -h parameter to invalidate the X invalidate pattern header containing the URL part of our ban expression. I've talked about the ban list and about ban expressions, but so far the ban list itself has been a very opaque thing. Time to change that and provide a bit more transparency. You can show the ban list by running the Varnish ADM ban.list subcommand. When the cache is empty, this is what it looks like. There's always one ban present. Its creation is represented by this Unix timestamp. The next attribute is the ref counter, which is a numeric value. In this case, 0 objects are matched. And if the last attribute is C, it means the execution of this ban expression has completed. Let's add a new ban and call Varnish ADM ban and use the expression object.status is not equal to 0, which is another way of saying remove every single object from the cache. And when we display the ban list again, you'll see that the new ban expression has been added. Its ref counter is 0, and that means no new objects have been added to the cache since this ban expression was added. There is a dash instead of a C, meaning this expression hasn't completed yet. But the row below, the older one, the ref counter has increased from 0 to 3, meaning that this object.status differs from 0 expression has matched 3 objects so far. And eventually, the ban will be completed, the older one will be dropped from the list, and new objects might enter the cache. As you can see here, the ref counter is 1. Here's another example where 2 more bans are added to the ban list. The ref counter of the initial ban expression is set to 9, meaning that the newly added one will have to match 9 objects. And its own reference counter is set to 0, so that means the newest of bans has 0 new objects to match. And that makes perfect sense because there's only an 8-second time difference in between the addition of the first and the second of the new bans. But after that last ban expression was added to the ban list, 2 new objects were added to the cache, which increases the reference counter of the last ban. And it's in fact the ban lurker thread that is responsible for processing these bans on the list. It's in fact a thread that runs continuously and at set intervals processes a number of bans. So let's look at the runtime parameters that allow us to decide when the ban lurker does what. Here's a list, and it starts with ban lurker age, which is a setting that defines the minimum age of an object before it's considered for cache invalidation. And that default setting is 60 seconds, meaning that an object should at least be 60 seconds old before it can be removed from the cache. The next one is ban lurker sleep, and it defines the intervals with which the ban lurker looks at the ban list to process the bans. And its default value is set to run every 10 milliseconds. And if your ban list is getting quite long, the ban lurker batch setting will limit the amount of executions within a single iteration. The default value is set to 1000, meaning that only 1000 bans will be executed on every run, while duplicate bans are being removed by enabling the ban_dup runtime parameter. Now that might come out the wrong way, I'm saying only 1000. Having 1000 bans on the list is quite big, and given the right circumstances, banning can become very CPU intensive. And those circumstances are reflected by the number of objects and the number of ban expressions on your ban list. The number of operations that needs to take place at any given time is the number of objects times the number of ban expressions, and that can get quite a lot. And at some point this becomes a performance concern. An alternative method to remove multiple objects from the cache at once comes under the form of secondary keys. This invalidation method is not URL centric. You can match keys other than the URL and the host header, and they execute a little bit faster than bans typically. The values of these tags or these keys can be set in the response header, or in VCL if you're using vmod ykey. This entire workflow is 100% compatible with your existing purge and ban logic in VCL and requires you to use one of two vmods. If you're using Varnish Cache, you can use vmod xkey, which has a more limited feature set, and if you're using Varnish Enterprise, which is the commercial version of Varnish, you can use vmod ykey. Let's have a look at vmod xkey first. You can download the source code of vmod xkey from github.com/varnish/varnish-modules. And yes, it's source code, so that means you have to compile it from source. There could be packages in the future, but for now they're not, so it might be a bit inconvenient. You can leverage the xkey response header in your HTTP responses to set the tags. You can store one or multiple ones as a secondary key, and yes, there's both hard and soft purge options available in vmod xkey. Let's have a look at some VCL code. The first thing we're going to do is import the xkey vmod once it's compiled, but we'll also import the standard vmod, which is a module containing some utility functions. There's always similarities to our initial example, so yes, we'll define an ACL, which is called purge, and we'll define the necessary logic in VCL receive, which matches the purge request method, which matches the client IP to the ACL and returns a 405. Here's a nice backwards compatibility trick. We rely on the xkey purge request header to inject the necessary keys that we want to invalidate. If that header is not set, well, we'll just fall back to standard purge behavior and use the URL and the host header to invalidate a single object. But if it is set, we can call xkey.purge and perform the purge. We'll use the value of xkey purge as an argument in that function, and the return value is stored in xpurges. Xpurges contains the number of objects that we matched. We use the std.integer function to convert the string value of xpurges into a numerical value. And if the value is different from 0, it means we actually matched some objects. So we can return a synthetic 200 with the number of objects that we purged. If the value was 0, it means we didn't find the key and we return the appropriate 404. As mentioned, storing these keys in the cache is done using a specific header. But the first thing we do is set the cache control header to decide how long objects need to be stored in cache. In this case, that's 600 seconds or 10 minutes. And it's in fact the xkey header that we're using in the response to decide on the keys. We can have one or multiple ones. In this case, we have category sports, then we have the unique identifier as the second key, and the third one is type article. And we can invalidate all the objects that match these tags at once. Xkey doesn't offer that much flexibility, but you can use an alternative to the xkey header. You can use x-hash2 as the response header in which you want to store the tags. And instead of a space separator for your tags, you can also use a comma separator. That's another bit of flexibility it offers, but it's pretty much limited to that. Performing an xkey invalidation is very similar to what we've seen before. We use the purge request method. The URL doesn't really matter. And yes, while we have a host header, the magic is really in the header we're using. And you're free to choose which one that is. We've opted in the VCL for x-xkey-purge, which currently contains category_sports. This will match every object that has that tag and remove them at once. We can extend that expression and add multiple tags that we want to use for invalidation. The response could either be a 404 when the key wasn't found, it'll be a 200 when we can at least purge one object, but the added value of secondary keys is the ability to remove multiple objects from the cache in one invalidation call. And if regular XKey purges are a bit too aggressive for your taste, you can always use the soft purge function, which will set the TTL to 0 and maintain grace and keep values for potential asynchronous revalidation. And while XKey could be a good alternative for banning, there are some limitations though. Beyond the difficulty of installing it, there is no header name customization. You can't choose the name of the header with which you'll set the tags. There's also no separation customization possible. Now we have spaces, you could do commas, but beyond that, there's nothing you can customize about it. You can't tag explicit keys in the VCL code, so everything needs to come from the header. The entire architecture is a bit sensitive to locking, and while it's faster than banning, it is not super fast at large scale, and it's not built for the massive storage engine, which is Varnish Enterprise's custom storage engine, which led us, Varnish Software, to develop another version, which we call vmod YKey. And yes, YKey is the successor of XKey, hence the name. It is really fast and it also scales really well. And with scale, we mean executing these invalidations on huge datasets. It was optimized for the massive storage engine, our proprietary storage solution, and can operate on datasets of terabytes in size without any performance degradation. Here's some VCL code, not necessarily to show you how to invalidate the cache with YKey, but how to choose the header that assigns the keys. And in this case, we're using the ykey.addHeader function to assign the YKey header. And then here's the example of how to use the YKey header in your HTTP response to assign a category, which is sports, the unique identifier, and the type, which is an article. Let's go back to the VCL code and add some YKey specific logic. What we're going to do is add an explicit key called image, but only if the content type of the backend response starts with image/. So if that header is properly set to an image, we know it's an image, we can assign it as a key. You can even assign an extra header to maintain that compatibility with XKey. So in this case, we're ensuring that the XKey header can also be used to assign keys. Remember this? This is the VCL code we used to perform XKey invalidations. Let's do some minimal alterations to ensure that it supports YKey. The header that we'll use to mark the keys to invalidate is YKey purge. The YKey purge_header function is used to perform the invalidations, and it takes that header as well as a separator. We opted for a space separator, but you can turn that into a semicolon separator, a colon separator, whatever you want it to be. By default, regular purges are run, but by adding true as a third argument, we're enabling soft purges.
That was it. That was cache invalidation. I hope it makes sense to you, and I hope you appreciate the importance of it. Because again, removing objects from the cache in a timely fashion is just as important as storing objects in the cache. It's a bit of a trade-off, it always has been. Either you store as much as you can for as long as possible in the cache and have good performance, and the trade-off is, well, if you store objects for too long, you have data inconsistency. But thanks to purging, banning, XKey, YKey, and the other mechanisms we covered, you have a safe and consistent way of removing just the right content from the cache. So thank you for watching this, and see you next time for yet another video.